Okay, so we're going to show you a few experiments now which are based on some of the fundamental chemistry of the transition metals, and it's obvious to say, but there's some green solutions here in front of me, and these are actually solutions of nickel. Not just nickel, but nickel chloride dissolved in water. And when nickel chloride dissolves in water, it forms a complex. And we have the complex here on the flip chart. It's nickel surrounded by 6 water molecules. And these water molecules are what's known as ligands. They actually provide a lone pair of electrons and coordinate to the nickel atom. Okay, and you can see you've got 6 water molecules. And as a bit of revision for you now, we're going to work out the oxidation state of nickel. And it's actually quite simple in this case because water is a neutral ligand. Okay, it looks like that. It's got a V shape. 2 lone pairs of electrons, and one of those lone pairs will coordinate to the metal. Okay, but it's neutral. So looking at the complex, you'll see it's got a charge of 2+. So that tells you that the nickel oxidation state must be +2. And that's a very common oxidation state for nickel. The geometry of the complex is, as you can see there, it's octahedral. 6 ligands forming an octahedral complex, which is actually probably the most common coordination geometry you find for transition metals. And in fact, we have a simple model there of an octahedral complex. We're going to come back to that later when we start adding different ligands. Okay. So returning now to the oxidation state, what is the d electron configuration that corresponds to nickel 2? Well, again, you remember these are the electron configurations for the first row transition metals, starting from scandium, going through to zinc. Argon there in brackets, that's the configuration of the previous noble gas, argon, so that's a completely closed shell. They're core electrons. These are the electrons of interest, and as you go across progressively from element to element, we're adding another electron. So if we start with scandium, this comes straight after calcium. And calcium, you've filled up the 4s energy levels, so you have 4s2. You then start to fill up the d shell. So scandium is 3d1, titanium 3d2, vanadium 3d3. Then you remember you have this weird sort of situation that happens at chromium, where you actually half fill the d shell, effectively pinching a 4s electron to produce a half filled shell, which is this extra stable arrangement. You then continue to add electrons into the d shell as you go across the first row. But anyway, we're interested in nickel, or nickel 2+. So there's our nickel. The nickel atoms have got the electron configuration 3d8 4s2. And you'll also remember that when you go to the ions, you initially remove the 4s electrons. So nickel 2+ has to be 3d8. Okay, so there's a little bit of revision there for you on electron configurations and oxidation states. But let's go back to our solution, our green solution. Why is it green? Well, you remember for an octahedral complex, and I'll just return to our original chart. Okay, so that's the complex we're interested in. You remember in an octahedral complex, the d orbitals are split, and they're split into 2 levels. Okay, we can represent them like this. Okay, the lower energy set is called the T2G set, and the higher energy set is called the EG set. And electrons will occupy those energy levels. Those your d electrons will go into that split set of orbitals, and this is how they do it for nickel. Remember, there's 8 of them. So in fact there's only one way that the electrons could possibly go into those orbitals, and that's as shown there. You remember this energy gap here between the T2G and the EG set we call, if I can try and draw it on like that, delta O, or the octahedral crystal field splitting. So where's the colour come from? Well, it just so happens that this energy gap here, the delta naught, happens to fall in the visible part of the spectrum. And as a sort of aside, this very solution of nickel was used to define Beer's law. You remember Beer's law, absorbance equals molar extinction coefficient times concentration times path length. That was actually derived based on measurements, spectroscopic measurements on a nickel solution, nickel 2+ solution in water. So the reason it's green is because this energy gap falls in the visible region and you're exciting electrons from the T2G up to the EG energy levels. Right, so what we're going to do now is a bit of chemistry. Is demonstrate this reaction here. Nickel, 6 waters, 2+, that's our green solution, and we're actually going to do a ligand substitution reaction where we replace water. So let's have a go. There's our nickel 2 solution. We have some concentrated ammonia, and you'll notice if I just drip it in, we should start to see a colour change. It's going from green to this deep blue colour. Okay, I don't think there's any doubt there's a distinct colour change there compared to the others.